Any damage identified during inspection, including corrosion, is termed as a change from tank's original physical condition. Changes include internal and external corrosion, change in fluid, specific gravity, pressure, temperature, any settlement and distortion, any load from roof, seismic, and wind load. Tank roof evaluation. Roof support members shall be inspected for flawness, damage, and corrosion. Look for severe internal corrosion of pipe columns that otherwise not detectable by external visual inspection. Look for cracks and punctures of pontoon. For floating roofs, look at hinges and steel support for damage. Change of service. API 650 Annex M applies when the temperature exceeds 200 degrees Fahrenheit. If operating temperature is below the original design, brittle fracture may occur. Inspect vents for proper operation that prevents partial vacuum and collapse of tank. Tank shell evaluation. General or localized pitting corrosion may occur. Pitting is not normally a threat unless they are closely packed together. The actual thickness measured by UT thickness measurement or profile radiography minus the corrosion allowance is used to determine the liquid level. If the measured thickness is below the minimum required thickness, the tank shall be either repaired, derated, that means you cannot fill it up to that level that you used to be previously filled because it cannot tolerate the load, because the thickness, the design thickness is more than the minimum required thickness is more than the available thickness, or retired totally. Actual thickness measurement. First, determine the critical length L. L is equal to 3.7 DT2. T2 is the minimum measured thickness, excluding pitting. D is the tank diameter, and L the maximum vertical length over which hoop stress are assumed to average out around local discontinuities. Decide which area is most affected and draw parallel lines equal to the calculated length L. Minimum 5 readings you should take. So what happens is you first identify the area that's been damaged and then draw lines around that area, and the length L that you should take between that 5 readings is determined by this formula. Is 3.7 DT2 or maximum 40 inch. So the cap is 40 inch. Whatever you get should be less than 40. If it's more than 40, then take L as 40 inch. Take 5 readings at least. And this is a cross section of one of the readings. As you can see, there might be some, some places that you might have more less thickness. You might measure some more thickness. You might measure over this length L, and you average it out. You take at least 5 readings and average it out. That would be the minimum average thickness, T1. So T1 would be the calculated lowest average thickness. T2 is minimum measured thickness excluding pitting. So it will be, T2 will be single one, like this one is T2 here, and average of all the readings will be T1. So the minimum thickness that you get into diameter into 3.7 square root will be L, maximum 40 inch. That's to measure the L only. And there should be a few acceptance criteria here. One is T1, that is the minimum average thickness that you have measured along the worst case scenario, the worst line that give you the minimum average thickness, is greater than T minimum. That's a minimum required thickness. And the second thing is T2, the minimum one single readings that you took on any of these lines. This is a single reading. It should be greater than 0.6 T minimum. So only 0.6 times of T minimum it should be the minimum required thickness. And no single pit depth can be less than 0.5 T minimum. So no single pit depth should, every pit depth should be greater than half of the minimum thickness, single pit. But the average thickness should be always greater than minimum calculated average thickness should be greater than T minimum. The single thickness that you took out of this average should be greater than 0.6 times, and if it is a pit, then it should be 0.5 times. And also the sum of pits dimensions along any critical line is not more than 2 inch within any 8-inch length. So if you take a L here, on the L, if you see 8 inch, you take 8 inch of it, any 8 inch, any pits you see here, the area, the sum of the area in that 8-inch line, say if this is 8 inch from here to here, you have several pits along the line. The sum of the areas of these pits should not be more than 2 inch. That's what is the another requirement. Okay. So minimum thickness calculation for welded tank shell up to 200 feet of diameter. So this formula is up to 200 feet of diameter, otherwise it's not applicable. T minimum is for entire shell course. If you want to find the T minimum, is 2.6 into H-1 dg divided by SE. E is the joint efficiency, S is the allowable stress, G is the specific gravity. For example, for water it's 1, and D is the diameter, and H is the height of the vessel. And if you want to measure, see that for any specific location, then there is no -1 here, so it's straight away 2.6 HDG divided by SE. Now you can find the S from table 4.1, or go to API 653 and we'll see how these tables work. So if you go to API 653, so we start from table 4.1, so that when we continue, you know what we are talking about. Let's go to table 4.1. So as you can see here, this shows maximum allowable shell stress. This will be available to you during open book, so but you should know where you should go. This is in table 4.1, page 4.4-7. So if you see, this material A283C has got the minimum specified yield strength, 30,000 pound-foot per square inch of PSI, and minimum specified tensile strength, which is 55,000. But for lower two courses, so the first, second course from the bottom up is 23,600, and then upper courses you can apply a stress of 26,000, depending which course you're talking. Yeah. For allowable product stress, for hydrostatic stress, which is not permanent, for just test, for hydrostatic test stress, you can take the lower two courses. You can take, if the material is A283, is 26,000, and for upper courses 27,000. You see that it's slightly more than this. This is the working stress, and this is the test stress. So during the hydro test calculation, you should, because you remember, like if you know about the pressure vessel or piping, it's always the test is higher. It's like 1.3 times of, or 1.5 times of the maximum allowable working pressure, and hence you see here the difference. So first two cores, depending where is it, is 23,600, and upper course is 26,000, and lower two courses for hydro test is 26,000. And as you can see, there are different materials here, like A51660. It tells you the minimum yield strength, tensile strength, 30,000, 55,000, and allowable product stress is 23,600 for the first two courses, and then 26,000 for upper courses. And hydro test is 26 and 27 for lower two courses and upper courses. So this is a table. Once selecting the material, they tell you what the material is. You find the maximum allowable stress from here. Okay. And then we have, if the material is unknown, then you use the minimum one, which is A283, the mechanical characteristic of A283, which has got the minimum strength here, as you can see. As you go down, the strength increases. So everything you take according to A3. And if the joint efficiency is not known, then you take the joint efficiency as 0.7, the lowest joint efficiency. So read this because sometimes you need to, during the open book question, you might need to have this general notes here. And table 2 is about the joint efficiency. So what practically is saying that if it's built according to API 650 tank, 7th and later edition, 1980 to present, then for butt weld, you have if you use the full radiography is 1, if it's a spot radiography is 0.85, and if it is there is no RT is 0.7. And if it was older one, like from 1961 to 1978, then is 0.85, unless annexes D or G apply to that. Okay, so if it is it's built according to API 12C from 1957 to 58. If it's a butt weld, straight away 0.85. If it's a older one, 1940 to 1956, then it's 0.75. As you can see, if the older tanks get a lower joint efficiency here. And if it is unknown, then 0.7 straight away. And we go to other tables. For riveted joints, we might receive question from this. As you can see, if it's a lock joint, number of rivet rows is 1, is 0.45. If it is number of rivet rows, the row of rivets are 2, is 0.6. And if there are 3 and 4, they are 0.7 and 0.75. So maximum it is. And for butt weld, if it is butt joint, then it's if number of rows are 2, is 0.75 and so forth. So this is for riveted joints, table 4.3. If you go to table 4.4, so this shows the minimum plate thickness. So the minimum plate thickness cannot be more than 0.1 inch with no detection system or anything for containment, no dikes for containment of a bottom leak, or no detection system if there is a leak, then it's 0.1 inch. If there is a detection system or there is a dike, then the minimum thickness can be up to 0.05 inch. And if there is a reinforced lining for the tank, like thick coating, you can add 0.05 inch to the available thickness. So it can be eventually, the total one should be 0.05 inch. So in 2 occasions, it can be 0.05 inch when there is a leak detection, when it's got a lining, and when it's got a dike, the tank. Otherwise, the minimum thickness is 0.1 inch. And table 5, it shows annular bottom plate thickness for product specific gravity of up to 1, okay, which is water. So plate shell thickness of first shell course, if it is less than 0.75 inch, the shell course, first shell course, and stress in first shell course, and is less, the allowable stress is less than 24,300, then the minimum thickness should be 0.17, as you see here. Now, if you have a shell course that say the thickness is between 1.25 inch to 1.5 inch, and the shell course say is greater than 32,400 psi, the allowable stress, then it is the minimum annular plate thickness should be 0.959 inch. So this table shows you how that works. Now back to our what we were talking about. So we said for entire course is T minimum is 2.6 into bracket h minus 1 dg divided by se, and for a specific location is 2.6 hdg divided by se. As you can see, there is minus 1 here. You don't need to memorize this. They will give you, this is an open book question, so they would give you, but you know how where to go. API 653 chapter 4. And note that E equal to 1 at locations 1 inch or twice the plate thickness away from the well toe. So if you are 1 inch away, then the stress concentration at the toe well is not considered, and it's considered as a base plate 1 inch away from the toe well. It's not superimposed to that point. So anything 1 inch away or twice the plate thickness, you can take the E equal to 1 if that point is 1 inch away. And hydrostatic test height, how you calculate it after determining the control thickness. Control thickness for the entire shell course, HT is calculated as this. So you can do here, you can, if they give you in the exam 2 questions, like a question with 2 scenarios, you calculate the TM minimum for entire shell course and for a specific location. The deciding factor will be the lowest T minimum that you have calculated, okay? And then use that T minimum in this hydrostatic test, which is if you want to calculate the controlling, after determining the controlling, HT is calculated as follow. For the entire shell course, it would be 1 plus SE, ST, E, T minimum 2.60. And this would be for a locally thin area would be STE. So there would be no 1 here. So you can use T minimum for entire course and T minimum for locally thin area and determine the HT in both cases. H, if it is for the entire shell course, it would be from the bottom of shell course to the hydrostatic test height, which would be the whole hydrostatic test height. And if it is for a locally thin area, would be from that point up to the where you fill the water for hydrostatic test. It would be the entire height up to that point. So here you have to use the H for the entire. If for entire shell course, it will be the whole height up to the where you do the hydro test. That height it means. And if it is a locally thin area, it will be from that point until the this. So if that point is say 2 feet away, 2 feet, the height of that locally thin area is say 2 feet or 3 feet or 10 feet, you have to reduce that 10 feet or 2 feet from the whole height that is tested. So here the HT would be different for locally tuned area. And ST is the maximum allowable hydrostatic test that you can find. The operating and hydrostatic test height is directly proportional to a specific gravity of fluid. So if the specific gravity is more than 1, the height shall be adjusted accordingly. The adjusted height would be HT divided by G. So the height would reduce here, because if G is greater than 1, then HT is divided by something greater than 1. So the H would be reduced here, because you have more loading weight or static head here load. If hydrostatic test height is less than the operating or design height, then the operating height shall be reduced, because operating height cannot be more than the hydrostatic test height. So this makes sense, because hydrostatic means you're using the worst scenario, and you're also giving it practically you're giving it some factor, say 1.3 times like a pressure test of the maximum allowable working pressure. So here the operating height cannot be more than the test height, because test height wants to know that it validate that it can, or verify that it can actually withstand the load and for the maximum allowable working load. And so that should be more than the operating height. So if it is more, if you find that operating height is more, you have to reduce it to the test height. Because you can't use it more than what you have tested it for. Fitness for service, it is the actual, if the actual thickness of tank is measured to be less than the minimum required thickness, then a fitness for service evaluation API 579 shall be performed. And minimum thickness calculation for riveted tank shell, the riveted joint efficiency given in table 4.3 as we showed you. Allowable stress is 21,000 and E is equal to 1 for shell plate 6-inch or more away from the rivets. So remember there it was for welded joints was 1 inch away, or twice the plate thickness away from the weld toe. Here it's 6-inch or more away from the rivets. You can take a, if you want to calculate a localized so here E shall be equal to 1 for 6-inch away from the rivets. So it will be considered as a base plate. Distortions include weld misalignment, out of roundness, buckling, flattening, and could be caused by poor construction or repair, foundation settlements, wind load, etc., and should be evaluated on case-by-case basis. And remember that Annex M applies when the tank is operated at high temperatures exceeding 200 degrees Fahrenheit, but not less than 5 degrees Fahrenheit. Annex M of 650. Annex M basically advises reduction of allowable maximum stress that shall not exceed 0.8 Y, 0.8 times of yield strength for all shell courses. So in case the temperature is above 200 degrees Fahrenheit and up to 200 degrees Fahrenheit, the material strength does not change. Over that, it will reduce. So accordingly, it tells you that to be more onerous when deciding about the thickness and the allowable stress calculations. So it should not exceed 0.85. That's what Annex M says. When the minimum specified yield strength of the shell material is unknown, the lowest yield strength shall be taken. That is 30,000 foot per square inch, or 30,000 psi. If the tank diameter exceeds 100 feet and the tank was not constructed with a butt-welded annular ring, an analysis of the critical zone, which is an area within 3 inches away from the shell to bottom joint, is required. Bottom plate thickness measurement is done by UT thickness measurement or magnetic flux linkage. MFL can be set on a predetermined thickness to ensure that the minimum required thickness plus the corrosion rate multiplied by the inspection interval exists. So anything less than that thickness, you scan by MFL, it beeps or it warns you, and then you can zoom in and do more UT thickness measurement to find out the exact thickness of that local area. Release prevention barriers, as the name suggests, is aimed to prevent the escape of tank fluid contents. It may be made of steel, concrete, synthetic, clay, or a combination of them, with or without leak detection system. Minimum thickness for tank bottom, minimum required thickness is minimum of tank bottom thickness minus minimum required tank from the upper side minus which OR here is so basically this formula, what is saying that minimum remaining thickness is basically the minimum remaining thickness from the bottom side or bottom internal or bottom top minus the next inspection interval multiplied by the corrosion rate for the bottom side plus top side of the tank bottom. So this is what this formula is saying. Corrosion rate from is a corrosion interval multiplied by corrosion from the bottom and from the top. If the bottom has an internal coating and can survive during inspection interval, then no internal inspection corrosion is assumed, and hence this STPR will be 0. Similarly, if there is an effective protection and there is no bottom side corrosion, this one UPR will be 0. The bottom shall be repaired, lined, or replaced if it is calculated that the remaining thickness by the next inspection interval would be less than the minimum required thickness. So this is obvious what it says. Minimum thickness for annular plate ring, the minimum bottom thickness plate in the critical zone of the tank bottom can be smaller of either half of the original bottom plate thickness or half of the lower shell course minimum thickness, but not less than 0.1 inch. So as it says, and then according to table 4.4, bottom plate minimum thickness shall be at least 0.1 inch without release prevention barrier or leak detection, and minimum 0.05 inch with release prevention barrier or leak detection. And then table 4.5 that we showed shows the annular bottom plate thickness versus the stress in the first shell course or for product specific gravity up to 1. And most of the hydrocarbons, the specific gravity is less than 1. You do not need to memorize, but you should know where to look for the relevant exam question when it pops up. It's API 653 PP 4-16. Tank foundation evaluation. The main causes of tank foundation deteriorations are settlements, calcinating, or concrete drying, which when concrete dries it cracks, cracking, attack by water, acid, and frost and erosion. So these are the main causes of tank foundation, which is normally concrete. Anchor bolts can be distorted because of concrete settlement or tank uplift.